So basics of probability, and we'll get to these important notions of conditional probability and independence. So to start with, you have a set of experimental outcomes whose outcomes I'm going to mark at by psi1, psi2, etc. And in dealing with probability, the whole idea is that the experimental outcomes are random in nature. In other words, it's impossible to predict what would happen when you perform an experiment. Nevertheless, we can, through experimentation or through reasoning, we can figure out the probabilities of elementary outcomes. So the simplest example is tossing a coin, in which case the experimental outcomes are either head or tail. And we know that through experimentation or otherwise, if the probability of obtaining a head is, if the coin is fair, is half. Otherwise, we would denote it as P. And the probability of getting a tail is the remaining of that, which will be 1 minus P equal to Q. So in case the coin is fair, both are half, etc. So of course you have elementary outcomes. Then you can use the elementary outcomes to create more complicated events. I'm going to call A and B, etc. So this, so the question is, how do you figure out the probabilities of more complicated events from elementary events, etc. So we'll start. So you can see that set theory becomes important. Set theory, as you know, a set has got a subset has got elementary outcomes like this. Some of them, it doesn't have to be ordered, etc. So A and B are subsets. Then you have the union. So by union we mean if you have A here and B here, union is the set of elements that belong to A union B, both A or B. So that will be A union B. Similarly, you have, so this is A union B. A intersection B is the set of elements that belong to both A and B. So that we denote it this way, or A intersection B, or simply as AB. So these are the elements that belong to both A and B. This is A or B. Then there are set rules. A union B complement is A complement intersection B complement. And A intersection B complement is A complement union B complement, etc. So these are De Morgan's laws, and you can verify by simply or through the Venn diagrams. These are Venn diagrams. And A complement is, of course, all the elements outside A. So if this is A, then A complement is everything outside A. And the notion of mutually exclusiveness means that A and B have nothing in common. So that means A intersection B. So we say A and B are mutually exclusive if A intersection B is the null set. So with this we can look at, so the question is, how do you assign probabilities of complicated events like A union B from simpler events? So we use the axioms of probability. So there are 3 axioms. There are 2 of them are self-evident. It's simple. The first axiom simply says that the probability of any set is non-negative. So that's obvious. And the second axiom says that something must happen. Probability of the whole set. If you perform an experiment, the probability of the whole set is 1. You essentially say something must happen. In other words, if you add up all the so one of the elementary outcomes must happen. So the whole set is 1. The third one says that if A and B are mutually exclusive, so it's a situation corresponding to this. So graphically, it would be like this. This is A, this is B. Here A and B are mutually exclusive. Then the probability of their union is the sum of the probabilities. So this is an axiom, so it's sort of self-evident. So 3 axioms. And the third one you can see from here. So for example, you can see from, so the union of this would be this, this together with this. The probability of that from the third axiom is the sum of the probabilities. Now we should use this to derive the probability of any one of them, all the other events. So for example, what is the probability of A complement? So this would go like this. A union A complement is, this is true for any set. If you have a set A here, and this is A complement, so their union would be, of course, the whole set. And moreover, they are mutually exclusive. That's another observation. So we can use the axiom. So probability of A union A bar. But A union A bar is also probability of the whole set. And from axiom number 2, that's 1. So this is using axiom number 2. But on the other hand, if you use axiom number 3 here, since A and A bar are mutually exclusive, then the probability of their union is the sum of the probabilities. So this is equal to 1. So from here, of course, you get probability of A bar is 1 minus PA. So I used something like this when I explained earlier about tossing a dice. So in a dice, you have only 2 outcomes, head and tail. So they cover the whole set. So head union tail is the whole set. So probability of tail is 1 minus probability of head. So we can also use this to compute. So the natural question that comes up is, what if A and B are like this? They are not mutually exclusive. So because this section, so here A intersection B is not empty. If A intersection B is empty, we can use the third axiom. What if they are not empty? So then we go like this. So somehow to compute this, so the question is, in that case, what is the probability of A union B? How do you do this? So somehow we have to make use of these 3 axioms. So easiest way is, the first step is to rewrite A union B as the intersection. So you can see from the diagram, A union B is this whole region. We want to rewrite this as the sum of, if possible, 2 mutually exclusive sets. So you can see that, so you have A here, then you have this region. If you can figure out this region, this is A. And if you see this, this is A bar B. So you can also write from here, you get, because this is A, everything outside A intersection with B would give you A bar B. So A bar B is this region. So A union B is A union A bar B. The interesting is these 2 are mutually exclusive. So if you want the probability of A union B, we can write this as probability of A union A bar B. But this being mutually exclusive, we can use axiom 3 to write this as PA plus PA bar B. Now, so the question is it possible to simplify this any further? So another idea is that A union A bar, of course, is the whole set. This is the whole set. So if you take intersection with B, whole set intersection with B, so whole set is here, and B is here. So whole set intersection B is B itself. So this is B itself. But on the other hand, if you use the distributive law here, you can also write the left side as AB union A bar B equal to B. So this is another identity. This is not surprising you can also see this way. This is A, so all we are doing is we are rewriting B as A bar B, and this region. This region is of course AB, and this region is A bar B. So this is just a decomposition of B, except that these two are mutually exclusive. So I can once again write the, bring in the third axiom. So this says PB is probability of AB union A bar B. But once again, using the axiom number 3, this is PAB plus PA bar B. Remember, we have been looking for this PA bar B, so we have a new equation. PA bar B is PB minus, from here, PB minus PAB. So I'm going to substitute that into this top equation. So you get PA plus PB minus PAB. So this is a useful identity. I'm going to rewrite it here. PA union B in general is PA, a probability of A plus probability of B minus probability of A union B. And so on. So we can, so this is an example to show that to compute the probability. So here it is not A union B, A intersection AB. In other words, I'm simply substituting this expression. So the A union B has been simplified in terms of A and B and the probability of A intersection B. Let me come to, so we'll proceed using, the whole idea is to show that we'll proceed using the axioms to compute any probabilities that we are interested in. All right, so this brings me to the notion of, we can introduce two new ideas or notions. One is on, two important notions. One is on conditional probability. So, and another one is independent. So let me sort of do it together. So we have, about some experiment, we have some idea. We know, let's say, PA. Then some event B occurs. That's the, so we do an experiment and we observe something. So we know that for sure something has happened. So the question is how to update our knowledge about A remember, event A, all events are sort of random or unpredictable. But here in this context, something has happened. What has happened is B has occurred. Given B has happened or occurred. So for that, we would bring in the notion of independent, notion of conditional probability. So conditional probability tries to address this question. You have some idea about A, but we know that something has just occurred because we saw it or we performed an experiment, we found the outcome to be B. So the question is, what can you say about A given that B has happened? So that's known as the conditional probability of A given B. So this is the conditional probability of A given B. So we are going to define this as PAB divided by PB. So that's by definition. So the question now is this the probability? All we have to do is, does this satisfy these three relations? So 1, 2, 3. Does it check? So let's check one by one. One is a probability of, any probability should be non-negative. This is ordinary probability divided by an ordinary probability. We will assume PB is greater than 0. So of course 1 checks because non-negative divided by positive is non-negative. Now probability of the whole set. So I'm going to replace A by S. By definition this is SB divided by PB. But SB is B itself, so PB over PB, and that's 1. So 2 also checks. So third is I take 2 sets which are mutually exclusive. So I take something like this, A here, C here. A and C are mutually exclusive. Let's say B is something like this. Okay. So we have A and C mutually exclusive. Then the conditional probability of A union C given B, that's what we want. So I'm going to call this to be D. So this is PDB divided by PB by this definition. So this is definition number 4. But D is A union C. So P of DB, PDB is D is A union C intersection B. So this, if you expand, you get P AB union BC or CB. And remember, look at the diagram. A and C are mutually exclusive. So AB, which is here, and this is BC. So this is BC. This is AC. They are mutually exclusive. AB are mutually exclusive. These two are also mutually exclusive. So by ordinary axiom number 3, this is the sum of the probabilities here. So that's going to be PAB plus, this is by axiom number 3, PCB. So I'm going to substitute this into the numerator here. So numerator is PDB. PDB turns out to be PAB plus PCB divided by PB. So this I can write as PAB divided by PB plus PCB divided by PB. But now if I use the conditional definition, remember PAB by PB is PA given B. So this will turn out to be PA given B. That's this one. And this is PC given B. So this is PA given B and PC given B. So it checks. The axiom number 3 also is true. So whoever came up with this definition for conditional probability, this one satisfies all the 3 original axioms. So this is a legitimate way to update A about, so how to update the answer is this way. We go through PA given B, which will be PAB divided by PB. So this is the way we are going to update the information. Now, another notion that is sort of complementary to the conditional probability is the notion of independence. So let me introduce that, and then that will give us a few tools to look at some interesting problems. So conditional probability is the way information is updated about an event. So in this spirit, I want to bring in the notion of independent events. So we say A and B, two events, A and B are independent if probability of A intersection B is the product of their probability. So remember, this is a probabilistic notion. So you cannot represent this using Venn diagrams. So PAB is, so this is the definition. Now it's easy to show that if A and B are independent, A bar and B, if A, B are independent, then it's easy to show that A bar, B, etc. A bar, B are independent. A bar, B bar are independent, etc. So let me show one of these quickly. So we start with this. The whole point is we know this is true. So I want to show for A. So remember, A union A bar is the whole set. So if I take the intersection with the B, this is just going. It's mutually exclusive. So using axiom number 3, this is PAB plus PA bar B equal to PB. We had this before, but now this is where we can use the given information. PAB is PA plus PA multiplied by PB. Here I just substituted for here. So plus PA bar B equal to PB. So I solve for PA bar B. So that's PB minus PA PB. So PB is common, so I pull out PB. So then what remains is 1 minus PA multiplied by PB. But we saw this is PA bar. So we got to show that these two are independent because the probability of their intersection is the probability of their product, etc. So you should be able to show that these two are independent by similarly going one more step this way. So that's the notion of independence. Notice that if you combine this, you get another interpretation of conditional probability. So if two events are, if A and B are independent, then see what happens to the conditional probability. That means that says then conditional probability of A given B is by definition PAB multiplied by divided by PB. But if A and B are independent, the numerator is PA multiplied by PB divided by PB. So PB cancels and you get PA. That means the conditional probability is the same as the unconditional probability. So that makes sense. If A and B have nothing to do with each other, if they are independent, knowing that B has occurred should not improve our knowledge about A. So this is also another check that both the definitions are sort of compatible. It goes together. You could also define conditional probability just using this line, saying A and B are independent, saying that A and B are independent if the conditional probability of A given B is the same as PA. It's one and the same. You will come back to that expression for PAB. So what this already gives us enough tools to derive a very important result in probability. So first of all, rewriting the conditional probability. So remember, conditional probability is A given B is PAB by PB. So from here you get PAB is PA given B multiplied by PB. Oh, this is 1. Let's say this is 2. So I could write PB given A also just by flipping A and B. So this will be PBA, which is the same as PAB divided by PA. but this is the same as AB is the same as BA, A intersection B. But here if you cross multiply, you get PAB is PB given A multiplied by PA. So this is, so now if you concentrate on 2 and 4, we get an interesting, so left side is PAB. So these two must be equal. So if we get an interesting result known as Bayes' theorem by simply equating. So we have PAB is PA given B multiplied by PB, or PB given A multiplied by PA. So we can rewrite this as, if you want, PB given A as PA given B multiplied by PB over PA. And this one is known as Bayes' theorem. So you may say, what's the big deal? So as I'm going to show you through an example, you can use this to make predictions and update your, a whole theory, set of theory has been developed based on this idea. But before I go any further, notice that, let me rewrite the Bayes' theorem in a slightly different way. Suppose I represent the whole set in this manner. So what you can see is that the whole set is represented by as the union of a bunch of sets. Interestingly, these sets, as I have drawn, they have nothing in common. So they are also, BI intersection Bj is empty. So this is known as a partition, because we are partitioning the whole space into no overlapping stuff. So because the partition, they are mutually exclusive, these sets are mutually exclusive, from here we get to the probability of the union is the sum of the probabilities. Equal to 1, right? You also get, so that's another property of the partition. Now suppose A is like this. This is A. So let's rewrite B for any BI. So here we also get, if you want, BI. This relation is true, right? So notice that because all the BIs form a partition, from here I can also write, so B1 union B2 union etc. Bn, or this is the whole set. So intersection with A is the A itself. So the left side you can write it as AB1 union AB2 etc. union ABN is A. So we get probability of A is summation of, because these are mutually exclusive. So the probability on the left side is the sum of the probability. So this is probability of ABI, I equal to 1 through n. But ABI itself, using conditional probability, we could write it as A. Let's say I'm going to do the summation on JBJ, probability of BJ. So this is just a summation, so I can change it to any index I like. I don't want to confuse with the BI there. So I can take this expression and plug it into the denominator. So if you want, this is another way to write. The numerator, of course, stays the same, divided by summation probability of A given Bj multiplied. So both are Bayes versions. depends on the problem. So I'm just going to call this result as Bayes' theorem. So let me show a quick example where this will be useful. So let's take a switch problem. Let's say there are 3 switches. So switches can open or close with, so the switches S1, S2, S3. So let's say identical switches, they close or open with a certain probability. So let's say switch AI represents the event that switch SI is closed. Then I'm going to define that probability of the switch being closed is P. I can call it Pi, but let us make it simple. So switches close or open independently. So in other words, the switches operate independently. What all that means is probability of Aj is Pai multiplied by Pj, which is P squared, etc. So the question is, what is the probability that an input signal is received at the output? So when will you get the signal here? So remember, the switches operate at random. So we have no idea whether the switch is open or closed, any one of them. But of course, a signal will only pass through if there is a path. So this is the way we argue. There need to be a path. That means for a path to exist, at least one of the switches need to be closed, or 2 could be closed, or all 3 could be closed. And so that gives, so if so what we are interested in is R. R is input signal is received at the output. So the question is, what is the probability of R? That's the first part. So the first observation is that, as I just said, we look at the problem, we try to, so R is the whole point here is R is a complicated event. So we try to write R in terms of the simpler events, which are switches operating at independently, etc. So this is one version of Bayes' theorem. So as I said, for the input to receive at the output, the switches need to be closed.